We look now at a new class of compounds of interest to the forensic chemist, having moved from carbohydrates and examining their ability to reduce other ions. We now look at proteins and ultimately DNA. You may have some experience with proteins. We're used to hearing about the importance of getting protein in our diets. We may also have heard about medical deficiencies when proteins are lacking and the resulting issues that occur from that. What we're interested in forensic chemistry is basically the structure and function of proteins, and then we're going to look at how we can test for different proteins. Firstly, there are two classes of proteins that we're interested in. The first kind of protein is called a fibrous protein. Now, fibrous proteins are structural proteins in living organisms. In other words, they're molecules that tend to make up that organism, that are involved in the structure, the physical aspect of the organism. For example, keratin is a protein that you tend to find in skin and fingernails and horns and feathers. It's got that fibrous structural component. Likewise, you would have heard of collagen, another example. You find collagen in tendons and cartilage and hides. If you wiggle the end of your nose, we're used to finding cartilage there. Likewise in your ears. This is a structural protein. Fibroin is a silky fibrous protein that is emitted by silkworms, and as a result of the complexity of fibrous proteins, we find that they tend to be tough, they're stringy, and they're insoluble. So they're a little bit like if you wanted to compare them to cellulose. Though cellulose is not a protein, we know that it too is tough and it's stringy and it's insoluble due to its complexity. Likewise, these fibrous proteins tend to be insoluble due to their complexity and structure. Now, the second type of protein that we're interested in forensic chemistry is the globular protein. Now, globular proteins tend to be functional proteins in living organisms. In other words, they're involved in the basic functioning of the organism. They're necessary for the organism's survival. One such example is insulin. Now, this controls blood glucose levels. Of course, organisms or people that struggle to control blood glucose levels usually do so due to a lack of insulin, and so these people are a form of diabetics. Hemoglobin is in fact a protein, and it's largely responsible for the transport of oxygen throughout the body. Antibodies contain, and some in and of themselves are proteins, and they fight disease. And enzymes, there are many protein enzymes that act as biological catalysts. Now, all of these globular proteins tend to be soluble and they're spherical, much like we saw the globular nature of amylose. These are also spherical in nature. They don't draw out into long stringy strands like the structural proteins do. And the difference is, of course, that they're involved in the functioning of organisms rather than the way that they are made up structurally. Now, with those two classes of proteins, we need to go and have a look at what the proteins actually are. Proteins are essentially polymers, and we're going to see that they polymerize in the same way that we're used to seeing so far in the chemistry course. Proteins are very complex in their structure, and they're polymers of amino acids. Now, you may have heard about amino acids. Now, amino acids in the forensic course, therefore, are the building blocks of proteins, and these polymerize together to form the protein structures. Now, let's have a look at amino acids, because they are the monomers of the polymer proteins. Amino acids derive their name from the parent compound ammonia. Now, you're familiar with ammonia. Ammonia is NH3. Now, NH3 is a nitrogen atom bonded to 3 hydrogens with a lone pair of electrons. If one of the H atoms in the ammonia compound was replaced by another carbon-containing group, now the resulting molecule would be known as an amine. Let's have a look at it happen. There's ammonia, the top left-hand of screen. NH3, you're used to seeing it. There's 2 electrons that are non-bonded that aren't being shown. They're of no interest to us in this segment of the course. Here's an amine. What we've done is we've replaced the leftmost hydrogen with what we're going to call an R group. And the R group can be any carbon-containing tail. And we'll have a look at some of these examples in a little moment. So R is just representative of this carbon tail. We're used to looking at R groups as alkyls, for example, non-reactive segments of a molecule. This isn't as true in proteins. We'll find that some of the tails are fairly reactive indeed. So once we've got our amine group, you can see that you have an NH2 segment of that amine group, and the NH2 is the functional group. It's the site of reactivity. Now what we're going to see is that amines are weak bases. In the same way that ammonia is a weak base, we see NH3 plus H2O will give you NH4 plus OH. In other words, the ammonia has reacted with the water molecule to form a hydroxide ion, therefore it's acting as a weak base. It has gained a proton. Amines will do the same thing. RNH2 plus water will form RNH3 plus the hydroxide ion. Therefore, amines behave in the same way as ammonia in solution. Now, amines are of vital importance when we're thinking about amino acids, because we'll see that they are half of the story. When an amine reacts with a carboxylic acid, the resulting compound is an amino acid. Just think about the name. Amine from ammonia, and it's NH2, acid because it's formed a new compound with a carboxylic acid. Let's see it happen. The amino acids are compounds that contain both an amine and a carboxylic acid. Let's have a look at a very simple one, glycine. Glycine is this molecule here. On the left-hand side of glycine, you'll see an H2N. You can now recognize that as an amine group. In the center is a carbon group, CH2. This is the backbone of all amino acids. And COOH is a carboxylic acid group on the right-hand side of glycine. There's your carboxylic acid. Here's your amine. There's a central carbon compound. This is an amino acid structure. Glycine is the simplest. We can represent further amino acids by using the R tail on that centralized carbon. Note now that there is only one hydrogen atom bonded to the central carbon, leaving one area of bonding available for the R group to attach. Now there's a whole family of amino acids, abbreviated AAs, that can be formed simply by altering the nature of the carbon chain, indicated as R on the diagram. Proteins are therefore long-chain polymers of thousands of amino acid monomers joining together. So the amino acid you can see there has the capability now of polymerizing, but it doesn't polymerize at the R group. We're going to see that the carboxylic acid and the amine group are the sites of polymerization. Now there are 20 different amino acids that can act as monomers for proteins, so you can imagine the variation. As you start to add different amino acids together, you're drawing from a pool of 20 and you can line them up in all manner of ways. Therefore we have many, many different variants and therefore many, many different proteins. Now here's a class of amino acids, and we would class this grouping to be amino acids with non-polar R groups. If you note the R group, for example, on alanine, here we are, we can tell that it's an amino acid because it's got an amine on the left, a central carbon compound, and a carboxylic acid on the right. Now the R group on this particular amino acid is simply the methyl group. Now that methyl group is a non-polar R group. In other words, it has no polarity. The carbon shares its electron in the bonding with its neighbouring hydrogens fairly evenly with no overall dipole. Likewise, glycine to the left of screen, it's just got a hydrogen, it's non-polar. Valine's getting slightly bigger side chain, but again, it's basically a hydrocarbon that you know are non-polar. And even phenylalanine, it's got a benzene ring, but within that benzene ring, there's no overall polarity. So these are all non-polar R groups. This will be of importance as we move through. Now we can get some amino acids that have polar R groups. If you have a look at aspartic acid, for example, Down the bottom, you've got your amine group to the left, your central carbon compound, and your carboxylic acid to the right, so it's an amino acid. But the R group is a carbon chain that has another carboxylic acid group. So in solution, that would actually ionize, donating the hydrogen to solution, lowering pH, and we would end up with a polarized group. Likewise, the amine group on the end of the R chain on lysine could potentially accept a proton and therefore ionize to form a positive tail on lysine. And so these are examples of amino acids that have polar R groups, groups that can potentially ionize and form a polar molecule. Thirdly, we have amino acids with polar R groups that don't form ions. For example, let's look at threonine in the middle. Threonine fits the mold of an amino acid. It's got the H2N, the amine group to the left, central carbon and carboxylic acid to the right. Then the R group going off the central carbon has an OH group. Now we know that the hydroxide group is a polar group, don't we? The oxygen unevenly shares its electrons with the hydrogen such that the hydrogen essentially acts like a raw proton. But the hydroxide group is not going to react any further in solution. It's tightly bound to that central CH, but it will have a polarity. It will have a slight area of negativity and a slight area of positivity. And even though it doesn't form an outright ion, it is polar. The other end of the R group is simply a methyl group that is non-polar. So we've got areas of both polarity and non-polarity on this R group of the amino acid. So there we go. We've got three groups of amino acids that are going to display different characteristics. We have non-polar R groups, we have polar ionized R groups, and polar non-ionized R groups. All are going to display different interactions at a molecular level. That looks like a funny word. Most people will refer to it as a Zwitter ion. Now, Zwitter ions really, if you want to think about a way to remember what they do, it can be handy to think of them as Twitter ions. And what does a twit do? Well, they talk too much. They just yabber on and on. They're forever changing their message. They're a bit of a twitterer, you might add. The latest phenomenon of twittering. I don't know if any of you Twitter, but a Zwitter ion is something that seems to sort of just twitter back and forward between different ions. Let me show you what I mean. Have a look. The COOH and the H2N groups pictured here are neutral. So COOH has no ionized charge yet, but it has the potential to. The amine group on the left has no ionized charge yet, but it has the potential to. What I mean by potential is that we know that in solution, the COOH group is called a carboxylic acid because it can donate a proton. So if we put it in solution, the following can happen. Note, the COO has lost its H and is therefore negatively charged. The H has moved from the carboxylic acid group over to the amine group. Therefore, that side of this amino acid is now positively charged, and the carboxylic acid side of the group is now negatively charged. And we're starting to get a polarity, one on each side, because in solution, that loosely held proton of the carboxylic acid is zwittering between the two tails. So the carboxylic acid, being acidic, tends to lose the proton, and the NH2, being slightly basic, tends to gain that proton in solution. Now, in solution, there is an equilibrium existing known as the Zwitter ion, and there it is represented. On the left, you've got your amine group, central carbon, R group, carboxylic acid. In solution, you end up with an equilibrium between the H3N, now that's polar, and the COO minus, that's polar too. This Zwitter ion is common for nearly all amino acids. They can exist as dipolar Zwitter ions in solution. So this just means that an amino acid placed into solution will automatically take on a polarity. This means at a observable level, amino acids tend to be crystalline solids. Why is this? Well, they act like an ionic solid. And we know that ionic solid, our classic case from the preliminary course, sodium chloride. Sodium chloride is an ionic solid. It has those electrostatic interactions. It forms a crystalline solid. Now, anything that's a polar crystalline solid tends to be water soluble because the polar water molecule can overcome the electrostatic force and dissolve it. And they also tend to have high melting points. It takes a lot of energy to overcome those electrostatic interactions. Now, pH can manipulate Zwitterion activity. This is not hard, it's just some basic chemistry applied to these amino acids. In low pH, an amino acid Zwitterion will do the following. Think about it first, picture it. If you had a Zwitterion in solution and you put it in a situation where there were a high concentration of protons, what do you think would happen? This is what would happen. On the left, you've got a Zwitterion. It's charged with a dipole, H3N on the left, COO-. You put that in an acidic solution, the H3N plus will keep its proton, and the carboxylic acid, because it's a weak acid, can take back a proton from solution, and you end up with an overall charge. This particular Zwitterion of this amino acid has become an overall cation because it's accepted a proton onto the carboxylic acid group that had originally donated its proton. Have a look at the overall charge on the right-hand side. The H3N plus exists as a positive area. The COOH is neutral, which means the overall charge of this Zwitterion is now positive in an acidic environment. It's no surprise that in a basic environment the opposite can happen. Note on the left there's a typical Zwitterion in solution. H3N plus, R group, COO-. If you put that in a basic environment, the H3N plus will donate its proton to solution, thereby neutralizing the hydroxide group and lowering pH. You then end up with an overall negative charge on your carboxylic acid group, which means that this has become an anion. It's donated its proton and is overall negative. Have a look at this example from the past 2006 HSC paper, and also take note of the exercises you can do on those pages of your textbook. 2006, question 33D simply asked this question. The structure of an amino acid glycine is shown. Identify the functional group A. Have a look carefully structurally at what you're looking at there. You've got an amine group on the left, it's NH2. You've got a centralized carbon, CH2, and then you've got your COOH structure, carboxylic acid. So the functional group A would be called carboxylic acid.